Okay, so lesson 4.3, and today we're looking at differentiating inverse trig functions. We're going to warm up with another Desmos activity. If you haven't done so already, follow the link and try and answer the question in the top left. Okay, so looking at this together, we have the black curve, which is a function f of x, and then we have the reflection of that in the line y equals x, the purple curve, which of course we know we could describe as the inverse, but it's not actually a function. But we're going to go along with it. We're going to be a little bit loose today, and we're going to try and think about the gradient of the inverse function in relation to the original. And this touches on what we were doing yesterday. So what we can see on the black curve is we have a coordinate of A, B, and then the tangent line in green on that original curve. And the question is, well, what is the gradient of the inverse here? And there's some options for us to choose from down the left-hand side. And if you played with this a little bit and moved the slider, one of the things you could have done is to monitor these different expressions and see which one seems to accurately represent the slope of the blue line, looking at when it's large, when it's small, when it's negative, and when it's positive. And then, of course, an alternative approach is for us to use a little bit of algebra, which we'll do now. So if we've got the original function, the black line, we'd say that is y equals f of x, and as part of that, we're looking at the coordinate AB. But to get the purple curve, what we've done is reflected in the line y equals x, meaning that our equation is now x equals f of y with coordinates of BA, because the x coordinate and the y coordinate have switched for all those values. And then it's this curve which we're looking at. So using the skill that we learnt yesterday, we could look at dx by dy, which is f dash of y, and then find the reciprocal of that for dy by dx, 1 over f dash of y, and then looking at the coordinate we're looking at on the purple line, the y value is a, so the expression that we think should match is 1 over f dash of a. And now if I'm looking at this one whilst I press play and change the x coordinate, I can see I have for this value a negative gradient that's getting steeper and steeper, then it turns to positive, but it's steep and then becoming smaller and smaller. And as we see it decrease here, it decreases to a given value around about 0.5, and then rather than getting any smaller, it's going to increase again until it becomes infinite, and then it becomes negative and steep. So our experience with Desmos backs up our maths, which is great to see. Okay, the next thing I want you to do before we go on to the notes themselves is I want you to consider these questions. And using exactly that same type of skill, what I'd like you to do is think about an inverse cos function. I'd like you to find dx by dy, and then I'd like you to switch it so it's in terms of x, and then I'd like you to find dy by dx. Give yourself a couple of minutes, off you go. Okay, so let's move to our notes. What we're going to do is we're going to fill in at the top here really our cheat sheet for cos inverse, sine inverse and tan inverse, but the first thing I'm going to do is I'm going to work through the same problem that you've done and complete the proof for the gradient of cos inverse. So using our method from yesterday, we're going to rewrite x as cos y, we're going to differentiate with respect to y, giving us minus sine y. And then using the hint that I gave you in that slide a second ago, I'm going to change my variable back to x by representing sine as the square root of 1 minus cos squared, and cos, of course, is x. So sine y I can write as the square root of 1 minus x squared. This means that dx by dy is minus the square root of 1 minus x squared. So dy by dx is minus 1 over the square root of 1 minus x squared. This gives us our first result, and one that we can fill in up here, minus 1 over root 1 minus x squared. And if we think about where this applies, well, the square root, of course, if we're talking about real numbers here, only applies if the thing in the square root is positive, which means that x has to be within minus 1 to 1, curved brackets, because if the denominator of the fraction is 0, then this is undefined. So, following that pattern, I think you guys should be able to fill in the other ones together, and I just realized I've written this in the wrong place. So, cos inverse should be over here. Don't think this will be the only time I make a mistake. And then what I want you to do is I want you to work out the values for sine inverse and tan inverse. And you can do your working out for tan inverse just at the bottom here. Give yourself a couple of minutes. Okay, so hopefully as you worked this through, but for sine, you realised that the only thing that was really going to change is we wouldn't have this minus sign here, because sine differentiates directly to cos, meaning that this wasn't a complete disaster. All I need to do is scribble out that minus sign, and this is correct. For tan, a very similar method, but of course a different identity. So just to run it through quickly, if x is tan y, then dx by dy is sec squared of y. And here we can see a little bit of a change, because like me, you might not be just so confident in your other Pythagorean identities, but we just derive them every time. Dividing by cos squared here gives me sine of tan squared plus 1 equals sec squared. So yeah, I knew it was something like this, but we can see a difference here, right? Because dx by dy now is 1 plus tan squared x, no square root, which means it's 1 plus x squared, no square root. Which means that when we flip it over, find the reciprocal, dy by dx is 1 over 1 plus x squared with no square root. And writing that up at the top, that tells us that, well, there's no issue with the denominator here. Any x value is going to give me a legitimate denominator, so the gradient of the inverse function is defined for all real values. I want you to think about the inverse function of tan, and to think, to cross-reference that idea with what you know about the function, that actually we can find the gradient of the inverse at all points. Okay, so hopefully quite simple so far. You'll notice the top of the next page looks very similar, but we've just introduced an extra parameter a, like we often see in questions. And what I'd like you to do first of all is I'd like you to think about how you can fill in these spaces. You've got room to do the proof for sine inverse, and what I just encourage you to do is to be quite careful about tan inverse. Don't get carried away. Okay, have a go, and pause the video, and then we'll go through it together. Okay, so hopefully you've had a go at doing these. I'm going to do it for sine, and we'll see that what impact this a has. And of course, like me, you're thinking that at some, you're going to multiply or divide by an a at some point and get an expression related to the previous one. But let's see where it comes out. Maybe it's not obvious exactly where that would be. So we rewrite with x as a sine y, and then we differentiate, giving me dx by dy is a cos y. And then a couple of different ways to do this, but what I think I'm going to do, what I think is easiest, is for me to take my standard Pythagorean identity and to multiply the whole thing through by a squared, telling me that a squared cos squared y plus a squared sine squared y equals a squared, which means that a cos y is the square root of a squared minus a squared sine squared y, or in other words, the square root of a squared minus x squared. Meaning that dy by dx is 1 over the square root of a squared minus x squared, taking the reciprocal because I'm inverting the differential here. So, here's my value. When is this valid? Well, the square root has to be positive, meaning that x has to be between minus a and a, otherwise we're going to get a negative number in the denominator here, and curve brackets because we cannot have the denominator equal to 0. So here's where the a pops up in the square root, and it's a squared, meaning that my first result is this one here. Thinking through the logic for this, the only thing that would change the cos inverse is that minus sign, as we'd expect, given the previous examples. So we're looking at the same result, but with a minus sign here, and for the same domain. But then for tan, I'm going to leave you to look at this yourself. We have a second a that appears. Maybe you were thinking after this that we're going to be looking at 1 over a squared plus x squared, but just take care here. The derivative of tan inverse of x over a is a over a squared plus x squared. And yeah, I would definitely make an extra note because this breaks the pattern that we're used to a little bit. And it's worth noting. So, those are the results we're going to apply today when we're doing all our questions, and we can learn these and take them to be standard results that then we can apply straight away without proof. So we've got a range of 4 questions here. I'd like you to try all of them, and I'd like you just to think about the fact that some of them we can do without proof, just by substituting in using the results at the top of the page, whereas others you might want to work through the question using a substitution. And in particular, there is a bit of a trick to the last one, and I want you just to take care when simplifying at the end. Give yourself a couple of minutes, have a go. Okay, so I'm going to run through these questions now. The first couple I'm going to do very quickly, because in this question here I'm looking at a equals 3, and I'm looking at the second example, so dy by dx is going to be 1 over the square root of 9 minus x squared, and that's going to be valid for x between minus 3 and 3. And for an example like that, nothing more to it really, we can use that standard result. For b, I'm also going to do a similar thing, but this time I notice because it's 4x, multiplying by 4 is the same as dividing by a quarter. So I'm going to say if a equals a quarter, then dy by dx would be minus 1, because it's cos, over the square root of 1 over 16, it's a quarter squared, minus x squared, which, just taking some care now, if I multiply the numerator and the denominator by 4, if the 4 comes within the square root, it becomes 16. So to simplify would be minus 4 over 1 minus 16x squared, valid for x between minus a quarter and a quarter. If you've got a little bit lost with the simplifying there, just take a second to pause this and work it through. But multiplying the numerator and the denominator by 4, bring the 4 inside the square root and it becomes 16. 4 part C, a similar kind of thing, and this time I'm going to let A be 3 over 2, and I'm looking at tan, so I just need to be careful about that A on the numerator. So I'm going to be looking at 3 over 2 over 9 over 4 plus x squared, and to simplify here, similar to before, I'm going to multiply numerator and denominator by 4, giving me 6 over 9 plus 4x squared, valid for x in all real numbers. Okay, so first 3 here, and I was able to do all of them using substitution into those formulas and just varying the value of a. But of course, you've probably noticed that things have changed a little bit for D. So, more challenging to see how this fits in with our example, and so our solution here is to try and use the chain rule with u equals x squared minus 1, meaning that du by dx would be 2x. So, if I do my block of 4, if I can squeeze it in here, this is where y equals sine inverse of u, so dy by du is going to be using the formula 1 over 1 minus u squared, and then applying the chain rule, dy by dx is the same as dy by du times by du by dx. So that would be 2x over the square root of 1 minus u squared, and u is x squared minus 1, so that's 1 minus x squared minus 1 squared. And I'm going to have to simplify that here, so looking at my square root, expanding this bracket, x squared squared is x to the power 4, I'm going to get a minus 2x squared, and then I'm going to have a plus 1, sorry, I need to multiply all of this by minus 1, don't I? Because the minus sign in front of the bracket, so minus sign in front of the bracket gives me minus x to the power 4 plus 2x squared, and then I'm going to get a plus 1 from the bracket, which is going to cancel, sorry, plus 1 multiplied by minus 1 giving me negative, which cancels with the 1 at the beginning. Sorry, that was a very clumsy explanation, but after I've done my cancelling, it's 2x over the square root of 2x squared minus x to the power 4. Okay, now here's the really clever bit, or the bit where we all make mistakes if we're not on the top of our game. So we can see that there is a factor of x squared within this square root here, which we want to bring out. So that will simplify our expression, but I need to be careful here because x can be positive and negative. So if I'm taking out that factor of x squared, what gets left under the square root is 2 minus x squared, got no doubt about that. However, what comes outside the bracket is square root of x squared, and I'm going to do this in another coloured pen. This might come up in all sorts of different contexts. What is the square root of x squared? The answer, of course, is mod x, because if x is negative this gives me the positive value, so it's modulus of x. Meaning that if I simplify what I've got here, I bring the mod x out, meaning that I have kind of plus or minus this, depending on when x is positive or negative. So let me write that down here where this is clear. That means if x is positive, then this modulus of x is just x, meaning it can cancel with the one above, and we have 2 over root 2 minus x squared. However, if x is negative, I have a positive value here, which is not the same thing as x. It would in fact be minus x, and so it's going to introduce an extra minus sign. So this was where x is positive, this is where x is negative, but you'll notice I haven't written that in yet, reason being that I need to check what my actual domain is. I have a square root on the denominator here, meaning this has to be positive, which means my domain has to be x between minus root 2 and root 2. The negative part of that is x within minus root 2 and 0. And the other part of that is x between 0 and root 2. So that's my solution for the final question here. I guess what you could think about, what I'll leave you to think about, is what happens when x equals 0. Think about substituting it into this value here and thinking about, into the original equation, thinking about the value and the gradient of sine inverse where x is 0. Okay, that's all good, hopefully, for you guys. What we can do just very quickly is have a look at the exercise. Exercise 6c here. I haven't put any of question 1 or 3 on the contract, and if you're really working hard at the moment trying to be kind to your future self and getting that extra practice on these fundamentals before things get tricky, I would really encourage you to do some questions from 1 and 3. But your contract is questions 2, and then a few of the questions later on as we move through the exercise. One thing that you're going to be asked to do at various points is find the maximal domain and the range of these functions, which will be a throwback to the work we did on circular functions. And then what we're adding to that is this ability to analyze the gradient function and to label turning points of the gradient function as well as the original function. So, and you can see us doing that for question 12 as well. So best of luck, and as normal, let me know if you have any issues. I'll try and do a review video of some of the questions from the exercise as well. Best of luck.